So as you've read in your lab manual, today we're going to be using a Hall probe to map out the magnetic fields that are generated by a coil or a set of coils. So just to quickly tell you about the Hall probe, now in class you probably have seen or will see the idea of the Hall effect. And what the Hall probe does is it takes the Hall effect and it comes up with a way of being able to actually quantify what the magnetic field is by measuring a potential difference, because after all, that's something we're really good at. So imagine I have a wire, and this is a big cross-section of a wire, and I have current flowing in one direction. Of course, it was the Hall effect that told us whether or not there were positive charge carriers or negative charge carriers, but I'll leave that story to 240. So here we know that there are negative charge carriers that are flowing in this direction. So if I have a magnetic field, let me put the magnetic field into the page here, then I can calculate the force on this charge, right? So the way that I would do it is I would do QV cross B and find out that this is generally downward, but since it's a negative charge, the force on this negative particle is going to be upwards, right? So this is the magnetic force here. So as these electrons are moving against the current, they're going to experience a magnetic force due to this external magnetic field that's generally upward. And the interesting thing about that is that then the electrons will sort of clump up at the top of the wire in the presence of this magnetic field, leaving effectively positive charges down at the bottom of the wire. Right? These aren't real, but it's sort of lack of electrons because the wire is made up of a bunch of metal atoms. Now, what we're left with is a potential difference. So if I measure the potential from the top of the wire to the bottom of the wire, I'm going to see that the potential difference here, the potential of the bottom of the wire is going to be higher than the potential at the top of the wire. And if I can calibrate that for how much, for the strength of that potential difference, or how big that potential difference is going to depend on the strength of the magnetic field, then I can use this measuring the potential difference across the wire as a way of telling us what the strength of the magnetic field is. Okay, and that's what's inside this probe. But there's an important part to this, and that is that our probes are going to be mounted on the ends of these PVC tubes, right? So you'll see that when I get to the lab setup in a second. But the Hall probes themselves are mounted at the end of these PVC tubes. But of course, the current through the Hall probe is going to be in some direction. Maybe if you look at this diagram, maybe you think it's upwards or downwards. The magnetic field can be pointing in any direction. Well, of course, the orientation of the magnetic field with respect to the Hall probe is going to be important because the magnetic force is QV cross B, right? The magnetic force is inherently three-dimensional. So you have to worry when you're doing this experiment, especially when we're doing something like calibrating the probes, that we keep track of the orientation of the Hall probe, right? If you rotate the Hall probe during the experiment, even we're not going to be measuring the same component of B than if you leave the Hall probe in one place. Now we've mounted them so that they should project out the Z component of the magnetic field, but they'll also have one of the perpendicular components depending on the direction of the current. Okay, so in short, don't rotate the Hall probe. It's important to keep it in one. It's important to keep it in one location. Okay, so the first thing that we're going to do is we're going to take a look at the magnetic field at the center of a single current carrying loop. So you move the Hall probe in and you put it at the center of the current loop. And now we want to be able to calibrate the Hall probe. So we need to be able to find out, well, what's the relationship between the potential difference measured by the Hall probe and the current flowing through the wire, which is going to generate the magnetic field. So in the lab manual, you're given an expression for the Z component of the magnetic field. You probably already saw this in Physics 240. If not, this is one of these great results that helps us to understand why why current loops have dipole moments. It's one of these great results that helps us to understand why the area of the loop is important when calculating the magnetic field. But it's an expression that sort of complicatedly depends on Z, right? And so by setting Z equal to 0 at the beginning, we're already making this equation easier to solve. but it also says that the strength of the z component of the magnetic field is proportional to the current, right? And so if I do this by changing the current at the center of the loop, I hope that the output of the Hall probe, which is this potential difference, is going to grow as a function of that current, right? So that I will get some plot that shows the larger the current, the larger the potential output of the Hall probe. And if I get a slope like that, if I get a line, if I get a graph that looks like a nice line, then I'm able to say that this output potential from the Hall probe is a good proxy for what the magnetic field is going to be. And that's the key to the first part of this lab, is that I want to be able to translate the output of the Hall probe to a magnetic field. If I get this line, that's an indication that I'm allowed to do that. And once I have this line, I can do some algebra to figure out what that conversion should be. So let's call the slope of this line m, right? So in this case, it's y equals mx plus b, right? Where m is the slope of this curve. If I think about my equation before, that the z component of the magnetic field is proportional to I, and this I'm evaluating at z equals 0. Well, if I also say the z component of the field is going to be proportional, so I'm going to put some constant of proportionality, kappa, in here, right? So it's going to be proportional to the potential difference v. Well, the potential difference I know is going to be m times I plus b, right? These are the m and b from the previous slide. So I now know that bz is going to be proportional to the current, which is proportional to the potential difference, and so I can combine those together and compare what this slope should be to what this slope should be. And so in this case, I know that kappa m is equal to mu naught n over 2 pi. And that's 2r, sorry. And that's going to allow me to solve this for kappa, right? And that's that translation coefficient between the output of the Hall probe to the z component of the magnetic field. And so once you have that kappa, now you can always plot the z component of the magnetic field, because you can convert that output potential into the z component. Now, there's this little issue of the y-intercept of that equation, and I'll leave it to you to think about how you should deal with that y-intercept. But of course, the argument that I've just made relies on the fact that the strength of the potential is proportional to the current. If you have a y-intercept, what must you have to do with that in order to compensate for it? Once you have that conversion, now you can use your Hall probe to measure all sorts of points along the z-axis, right? You can measure the magnetic field as a function of z, and then we'd be able to compare that to what you expect the magnetic field to be from the analytic formula. So when you get to lab today, almost everything is going to be set up for us. And that's because one of the tools that we're going to be using, the Hall probe, requires a certain amount of delicate wires to be connected together in order for it to function properly. You'll see that there's basically one circuit, which for me is on the left-hand side of the table, which has the Hall probe connected to a power supply and a digital multimeter. And on the other side of the table, you're going to have a power supply that's hooked up to another digital multimeter, and then our coils. So this setup over here, the setup that has the coil, that's the thing that's going to be generating the magnetic field. And this other setup connected to the Hall probe is going to be measuring the magnetic field. Now, we went over quickly how the Hall probe works, and so right now all I'm going to talk about is really how we get this thing up and running. So let's start with actually measuring the magnetic field. The Hall probe itself is located at the end of this piece of white PVC right here. And that's important to know where the Hall probe is, because we're going to be using it to measure the magnetic field, which is of course a field and therefore a function of space. And so you need to know where exactly in space are we going to be measuring the magnetic field. So that's located here at this end. At the other end, you'll notice that there's a very professional looking, actually it is quite good, connector that has 3 wires coming out of it. 2 of those wires, in my case the white and the black, are going directly to the Instec power supply, whereas the other wire, the green wire, is connected to my digital multimeter. Now, most of the times in this lab, what we've done with a digital multimeter is we've used it to record or to measure the actual potential difference that's coming out of a power supply. In this lab, that's not going to be the case, at least for this half of the apparatus. We're going to be using these Instec power supplies because they are our most reliable sources of potential. That is, the precision that this power supply has is higher than most of the power supplies that we buy, which is pretty high because we spend a lot of money here on power supplies. But basically, when you turn this on and you set what you want the potential to be, in this case, the top line here is 5 volts. We're going to, quote unquote, trust, with uncertainty, that the Instec power supply is providing 5 volts. Now, one good thing to do at some point during the lab might be to take a digital multimeter and plug it into this to convince yourself that the Instec is providing a 5 volt potential difference that, within whatever uncertainty you give it, is fairly stable throughout the lab. Okay. Now, the Instec power supply is one that you're going to use in your electronics class all the time. It has tons of buttons. It can do all sorts of output. We really don't want to play with much of that today. The reason that we're using such an expensive power supply to power the Hall probe is because we really need that very constant 5 volts in order to trust the output from the Hall probe. So when I turn on this digital multimeter, what it is actually measuring is it's measuring the output from the Hall probe itself. Okay, it's going to be measuring a proxy for the magnetic field in the Hall probe. Okay, so the important difference over here, the Hall probe is going to be measuring the magnetic field by giving us a reading on this digital multimeter, but this digital multimeter is reading the output of the Hall probe, not the potential difference of the Instec power supply. Over here, I have one of our Elenco power supplies, and these are ones that we've used now for weeks and weeks and weeks, right? So it almost needs no introduction. I have a digital multimeter set up in series so that the current is going to flow through the digital multimeter, so we're going to read it in terms of amps. Those amps are going to flow through our coils, and that's going to generate our magnetic field. Now, at one point in the lab, we're going to have 2 coils, and we're going to have to make sure the current flows through both of them, but this is enough for illustrative purposes. Okay? So you turn on this power supply, you can measure the current through it. That will allow you to create a magnetic field due to this current loop here. Each station also has a mounting rail. Okay, so you put your current loops on there and you tighten them with the screw that's in the front. You always want to untighten it a little bit before you slide it back and forth. The ruler that's mounted on this rail is pretty good, although you should convince yourself of that, and you should also use this to convince yourself of what the uncertainty should be. Now, the way that I have this set up is that my Hall probe is oriented so that it's exactly along the axis, and so if you were to look from above, you would see the PVC directly above the rail and exactly in the middle of the current loop. And that's how you want it to be, because the only thing that we're really varying in this lab, whether we have one coil or 2, the only distance that we're varying is where the loop is going to be in terms of the Hall probe. The other thing, of course, that we're going to be changing is the current through this current carrying loop, but we've already talked about that. Okay, so things to watch out for in the experimental apparatus. Make sure that your Instec is not set to anything fancy. Make sure that it's just putting out a DC potential difference. Make sure that this is monitoring the output from the Hall probe and not the potential difference across the Instack power supply. And over here, of course, make sure we're going to be putting amps worth of current through these wires, but make sure that you don't go above the tolerance for the lab. So that's about it for the experimental procedure. So at the end of the day, you're going to want 4 things. First, a plot of V versus I so that you can calibrate the Hall probe. Then once the Hall probe is calibrated, the rest of your plots are going to be in terms of the Z component of the magnetic field versus the distance. And we should have one for a single loop, one for the Helmholtz configuration, and then one for the anti-Helmholtz configuration. All right, that's it. Good luck.